Michael's out today because he's getting an MRI.
Okie dokie. So we were going through and starting to learn a little bit about the three-dimensional shapes of the molecules, and the idea behind it, or the main concept behind how we generate the shapes, or how we know the shapes and how they are formed, or whatever you want to think in that way, is that electrons are going to repel electrons, and so we want to put groups of electrons as far away from each other as possible. That's what it is, okay? And so what we always do, or what we'll end up doing, is looking at how many things are around a central atom, and then arranging those to maximize the bond angles in between, right? So that's kind of the simplified name of the game there. So in theory, you could construct any infinite number of geometries, right? You just have to find the best way to fit things around a central atom, and just, but the more you crowd things around, the less you can fit on there, that kind of thing, right? So that's kind of what we're going to be doing today, just kind of looking at, as you incrementally add electrons or atoms or change atoms for lone pairs and this kind of stuff, what are the different geometries and how do we identify those, okay? That's going to be the name of the game. But before we, before we get all into that, let's get started with prayer, and then we'll pick it up from there. But Lord, we just thank you yet again. Lord, we just thank you for another opportunity just to come before you, Lord, and just work through this day in the way that you would have us work through this day, Lord. Just help us to understand what it is that your task is for us today, Lord, and just in whatever way that might be, Lord, just clean our hearts and clean our mind just to see you a little bit better, Lord. Just focus our hearts onto what you would have us do, Lord, and just help us to walk on the path that you've set before us, Lord. We just pray for those people all around us and the people that you want us to reflect your light into their lives, Lord. We just pray that you give us that opportunity and that we can speak your words into their lives also, Lord. We just pray all this in your name. Amen. All right. So, what we had ended up with was, or that's basically what this slide is telling you guys here, okay? Put stuff around a central atom, spread it around, okay? That's what it is. All right, so this is a similar picture to what you guys have seen before, but this is probably the most important picture, okay? So we're going to be talking about different types of geometries. And I believe you guys talked about this or learned about this in lab this week, right? You guys learned about, what do they call it, electron geometries, or what do they call it? What is it?
Molecular.
Yeah, so molecular geometries and electron pair geometries, is that the two that you guys learned? Or what's the terms that you guys had?
No. Most of that lab has been confusion trying to find the computer.
Is that what happened? Okay, good. So I don't have to fight with different terminology then. So you guys will just use my terminology, and then that'll be just fine. But anyway, in theory, there's two types of geometries that we'll talk about. One is going to deal with everything, and the other one's going to deal with everything. Okay, that makes sense. Here's what I mean, okay? So we're going to learn about two different types of geometries, an electron pair geometry, or what I call electron pair geometry, or electron domain geometry might be another term. It's just basically asking how many total things are around a central atom, okay? And there's only ever going to be 5 answers for us, okay? And those answers are going to be 1, 2, 3, 4, 5, okay? Excuse me, 1, 2, 3, 4, 5, or 6, okay? If you have one, well, I guess we can't even say one. There's no such thing as only one thing around a central atom. But anyway, maybe let me start over here again. There'll only be 5 answers. And the answers will be 2, 3, 4, 5, or 6. You can either have 2 lone pairs, 2 atoms, 3 lone pairs, 3 atoms, right? Or 2 lone pairs, 1 atom, or right? Any of these kind of subservient derivatives of these numbers, okay? So here's what that really means for you guys. So when I ask you on an exam or a quiz, what's the electron pair geometry, you guys already know what the answer is, because there can only be one of 5 things. So it's basically multiple choice, okay? So you got a 20% shot at getting it right, and you got a 100% shot at getting it right if you guys can count to 6. Not seeing too much confidence in the audience. I don't know, guys. Okay? Do you guys get what I'm saying here? There's only ever going to be 5 answers for the electron pair geometry, and it all is based off of how many total things are around that central atom. Got it? Okay? That's all it is. Right? And so when I'm talking about my 5 answers, it's these guys on the left-hand side there. Okay? Linear, trigonal planar, tetrahedral, trigonal pyramidal, and octahedral. Okay? And so you guys hopefully see what I'm talking about there, right? The red atom is the central one. And you see on the top there you have 2 things around a central atom. Then 3, then 4, then 5, and then 6. Okay? So those are going to be your 5 answers for what the electron pair geometry is going to be. Either be linear, or trigonal planar, or tetrahedral, or trigonal pyramidal, or octahedral. Those are our options. Got it? We'll talk about what this stuff means in a little bit, right? But that'll become important also in just a little bit, so hang on to that, okay?
It looks remotely similar, or it looks remarkably similar to the electron configurations.
Yeah, well, that's where it comes from. Yep. Right? So electron pair geometries over here. Molecular geometries encompass everything, though. Your electron pair geometry can be the same as your molecular geometry. Okay? We'll talk about when and where and how that kind of happens. So if you remember, one of the ideas that I was trying to get across in one of the previous lectures was that we have our 5 dominant geometries here, and then everything else underneath here is what I call a subservient or a subset geometry. Okay, so what I mean is this. If you take a look at octahedral, right, we have a square pyramidal, square planar, T-shaped linear. Okay? All I'm doing as I move left to right is replacing one atom with one lone pair each time, sequentially. Okay? You guys with me on this one? So the molecular geometry just deals with how the atoms are arranged. And what I mean is this. So when I go up and talk to another chemistry person that I meet on the street, okay?
Does that happen a lot?
It happens on university campuses, right? So if I walk up to them and I tell them, hey, I just discovered a new molecule, right? And we're going to do our, our secret chemistry handshake so that we know that we're both chemists, right? And then he's going to say, all right, tell me about the geometry of it. And I will tell them about the molecular geometry. We care about how the atoms are arranged. Well, that seems to make sense, right? The atoms are kind of the things that do everything, right? That's where the nucleus is. The electrons are living around them, right? They get transformed, they get oxidized, they lose electrons, they gain electrons, they get all these things done, right? We care about where the atoms are. Well, let's think here for just a second. So if I only care where the atoms are, does that mean that my lone pairs magically disappear and they don't exist anymore? No. And that's the most common mistake that will happen. Okay? So when I ask you guys about the molecular geometry, I'm going to say, we only care about where the atoms are. And you guys are like, oh, okay, yeah. But you're going to forget that there's lone pairs there. Okay? Do the lone pairs disappear?
No.
No. Are they still influencing the overall geometry?
Yeah.
Yes. Okay? Because what did I say? There's only ever 5 big answers. As I replace lone pairs, you guys see how the shape is retained still? If you guys are just kind of looking at how many things are around it and how they're arranged. This is important. You guys see what I'm talking about with this? Okay, remember the shape is defined by how many electron things there are. When I'm looking at molecular geometry, I don't care about the lone pairs. That doesn't mean they magically disappear. Got it? I'm using my magic professor powers and I'm looking into the future. Okay? I'll ask you guys to tell me what the molecular geometry is, and your guys are going to forget about the lone pairs. Don't forget about the lone pairs. Okay? Don't do it. I don't want you guys to miss stuff. Everyone with me on this? Yeah, Gabe, what's up?
Do we have to know the
Your
names?
first day where you don't have your name tagged
Do you
on.
want me to put it up?
I do. All semester long, you've been the only one doing it, which I appreciate. The rest of you guys.
I forgot.
Okay. All right, now I'll answer your question. What's up?
Okay. Do we have to know the names of all of those
Yes.
shapes? So like the bent and the trigonal, pyramidal,
Yep.
all that stuff.
Yep.
Okay. We should be able to identify them depending on their number of potential atoms.
Identify them based on what?
Their potential atoms, like, which is the special numbers in the middle there, BSP stuff.
No. The answer is yes, but we'll make that link in just a little bit. The way you're going to identify them is just based on how many total things you have around it, and then how many lone pairs versus atoms there are. I'll break this down individually. It's the next couple of slides here, right? So my answer to you is yes, but we haven't talked about how to make that link quite yet. Okay? But don't worry, we'll get there. All right. So here's kind of my summary for what I was trying to get across for you guys there. Right? They can be described as their electron pair geometry or their molecular geometry. The difference being, do I count everything or do I only care about the atoms themselves? Okay? That's the only difference. Molecular geometry is by far the more commonly discussed geometry, but that doesn't mean that we magically leave off lone pairs or any of this kind of thing, okay? And right now you might be saying, well, why in the world does this matter, or who cares, or why do we have to do something like this? And I'll answer those questions for you. No, actually this is organic chemistry again. Right? So when you guys all get to OChem, right, then I'll start to, it'll start to make more sense why we deal with things in this way, okay? So for right now, you'll just have to take my word for it that the molecular geometry is the more important one, and don't forget about your lone pairs there, okay? So this is what I'm trying to say with this statement here. Right? Atoms can be seen, lone pairs are invisible. That doesn't mean that they don't exist, right? We don't see the air around us, but we all hope it exists in the next 5 minutes, right? Okay, same thing here with lone pairs. All right, so just a couple of statements here. This, hopefully we've already discussed most of this stuff, but just trying to put pen to paper. The actual geometry of the molecule may be different from the electron pair geometry. Really what I should be saying here is the molecular geometry of the molecule may be different than the electron geometry, okay? So what we mean by that is there's only ever 5 answers for my electron pair geometry. The molecular geometry may or may not be the same as that, okay? And that's what the rest of that chart is, okay? And I kind of try and give you guys a little bit of explanation down there.
Wait, so, sorry, Doc, just a question.
Yeah.
You said, maybe I misunderstood you, but I thought you just said that the electron geometry
Yep, electron pair geometry.
is the basic shape, and the molecular geometry.
Right, and you see they have different names to them, right?
So this is
But-
electron geometry.
Yes, those are only ever the answers for the electron pair geometry, but the molecular geometry and the electron pair geometry can be the same,
Okay.
right? And like I said, I'll be breaking this all down in just a second, okay? But you will never, let me back up just to make this a little bit more clear then. So again, right, these are only ever going to be your 5 answers for electron pair geometry. If I ask you guys on the exam quiz, whatever, right, what is the electron pair geometry, and you write down T-shaped, you're going to get it wrong. Okay, there's no such thing as a T-shaped electron pair geometry. Do you guys get what I mean with this? Can your molecular geometry be T-shaped? Absolutely. Can your molecular geometry also be trigonal bipyramidal? Absolutely. That's what I'm saying with it. Okay, molecular geometry has any of these answers up there. Electron pair, only the first 5. We good?
Mm-hmm. Thank you, Doc.
Yep. So the second bullet point here, right? The lone pairs affect the molecular geometry, right? Just because we say they're invisible, we don't see them, or whatever terminology the book wants to use with that, it doesn't mean that they don't influence the geometry. They are there. okay? They are there. They are doing their thing. They don't disappear. The only time they disappear is what? When you guys forget about them, right? There's an interesting philosophy lesson in there, right? Do things exist if you're not thinking about it? Right. Right? Lone pairs occupy space around the central atom, but are not observed as points on the molecular geometry. They're not seen, they're not cared about, whatever terminology you want to put there, okay? They're not included in the molecular geometry. Lone pairs on the central are, man, I feel like I'm missing a word in there. Lone pairs on the central atom because their electron density is close to them. I'm trying to tell you that, well, I don't know really what, I feel I'm missing a word in there. What I'm trying to tell you guys is that the lone pairs on the central atom are the ones that are going to define the geometry around that atom, okay? They exist exclusively on there, okay? They're the ones that are going to be influencing what's going on. Okay, now, with these lone pairs, they are going to affect the bond angles in a couple different ways. The most important way is that they're actually going to define the geometries of these things. And the second is they're going to have a little bit extra kind of oomph to push things around a little bit, okay? And we'll talk about what that means. But if you go back a couple slides, we said that lone pairs are going to take up the most space. Therefore, they're going to have the most repulsion, okay? They're going to push things around, okay? That's what I want you guys to think about. We want to minimize the lone pair repulsions is what it comes down to. All right. So the next couple of slides here, what we're going to do is just start breaking down the molecular geometry and the lone pair geometries and how they come together. And I'm trying to give you guys examples for each one of these here. So it'd be good practice for you guys to come back through and kind of make sure you guys get to the same answer that I can. Okay? So we're using that ax notation there, right, where the x and the e just represent atoms and lone pairs is all it is. Okay? So the first electron pair geometry is linear. That's when you have two things around a central atom. I don't care what those two things are, right? It could be one lone pair and one atom, or two lone pairs or two atoms. Right? We consider that a linear electron pair geometry. Okay? If we take a look at something like CO2, where we have two bonding pairs, okay? So two bonding pairs. What do we mean by a bonding pair? We're just talking about regions where things are bonded. Got it? Regions around that central atom. Okay? So if we have two regions that are bonded to atoms, something like carbon dioxide, right? That is a linear electron pair geometry and a linear molecular geometry. Okay? So that's where the overlap happens, when we have no lone pairs around the two atoms. If we switch to something like carbon monoxide, okay, we have a central atom with a lone pair and another atom, still two things around the central atom, still a linear electron pair geometry, but we only look at the atoms, okay, for the molecular geometry. But this is still linear, right? Because how do you connect two things? Well, you can only ever connect them in a straight line. Got it? So linear is kind of your easiest instance. Every answer is always going to be linear, right? If you have a central atom with two things around it.
So CO would not, the linear would not apply to the electron pair geometry.
No, everything in here, right? So at the top, if you have two groups, everything in here is a linear electron pair geometry. Right? Now what I do here is say, what if those two groups are atoms? What if it's one atom and one lone pair? Right?
So on CO,
yep.
it's still linear for both molecular and electron pair?
Yep.
Okay.
Yep. Couple more examples here for you guys. This one down here at the bottom. Right? It might be a little bit different from what you guys have seen before. What's different about that one on the bottom there? Yeah.
It has two central atoms.
Well, I don't know if we can have two things in the middle. So maybe, let me rephrase what you said there and say, we don't have necessarily a central atom. What do we mean by a central atom, though? Does your DNA molecule have a central atom? No, right? It's got a bunch of atoms in there. So what are we really talking about? We're saying when you guys are looking at a single atom, right? That's kind of your focal point, right? That is the atom that you're looking at, and everything around that is going to have a geometry to it. Does that make sense? So does it matter if I give you guys some stupidly complex molecule that has 15 atoms in it? No, we just do it on an individual basis. Got it? So what I mean is this. If I'm looking at this carbon atom here, how many things are around it? Right? This carbon atom here. I've got that, and I've got that. Got 2 things around it. Okay? This tends to be a little bit tricky for you guys. Right? Because when we say the term central atom, you guys think, oh, it has to be directly in the middle. No, we're just saying what atom are we looking at? Right? And everything that's around that. Right? What's the center of what you're looking at if you want to think about it? You guys following along with me on this one? Mm-hmm. Okay, good. All right. Linear, we got it. By the way, did I make a mistake up there on the top? Of my... What's wrong with that one on the top? Did I violate my octet rules? Right, beryllium doesn't have 8 electrons around. Is that a violation?
Does it want 8 electrons?
That's the question, right? So don't forget, what's the most important thing before we got into geometries here? Always checking your work.
Real.
Formal charges, right? So if you go through and check that, the formal charges are all good, okay? No mistakes. All right, so let's get into something a little bit more complex here then. So now let's deal with when you have 3 things, okay? 3 things around a central atom. So the overall electron pair geometry is trigonal planar, okay? 3 things in a plane around a central atom. Got it? If those 3 things are all atoms, okay, something like BCl3 over here, okay, that means the electron pair geometry and the molecular geometry are the same, okay? 3 atoms around a central atom, trigonal planar molecular geometry, okay? So the molecular geometry and the lone pair geometry are the same for this, okay? 2 atoms and 1 lone pair, okay? Now, we finally start to see a deviation from what we've had before, okay? The electron pair geometry here is still trigonal planar. Got it? The molecular geometry, I don't know why I pointed over there, molecular geometry is bent. Do you guys see where the name comes from here? Right, so if we're looking at just how the atoms are shaped, right? It's like you take a straight line and just bend it. Got it? Why is it bent? That's the question. Not why is the name called bent. Why does it have that shape?
Because those 2 atoms without the electron pair would just be linear. So that electron pair, or the lone pair, sorry, its volume or makes it sort of bends down a little bit. The repulsion theory.
Exactly. You guys catch this? Why do things take shape to begin with?
Because of repulsion.
The repulsion of electrons. You guys got it? Right? It takes a shape because how else can we fit 3 things around a central atom? Well, that's the only way, right? Basically in a triangle shape. That's the maximum space we can put in between them. Does that make sense? Okay. What's the angle that's in between all these atoms here then?
120 degrees.
120. Now, how do you guys know that? Well, we could think about it geometrically, right? I think I also gave you guys all the bond angles and stuff on one of the previous slides. Is it important to recognize
Yes.
that or is it important for you guys to know those bond angles? Absolutely. Okay. You got a question?
If lone pairs have the strongest repulsion, then why is the angle not smaller?
Perfect. That's where I was about to get. You stole my thunder. No, that is an excellent question, right? So, hey, wait a minute. In one of your other slides, you said that lone pairs take up more space than bonding pairs do. And since they have the most repulsion, how come they're not pushing everything else away from them a little bit more? And they are, okay? this angle isn't in reality exactly 120 degrees. It's slightly less than 120, okay? But when I ask you guys to give me the bond angles, I usually ask the question in a way of, give me the idealized bond angles. Got it? In reality, they're not going to be that. They're going to be different. Does that make sense? Okay. Lone pairs take up more space. They're just going to push everything else away from it. Got it? To this day, I still don't have a good example of a molecule like this. If you guys come up with something, please let me know. But so I talk about it here for completion's sake, but I really can't give you guys a good example of it. If we have one atom with two lone pairs around it, this again is a linear molecular geometry, right? So you ignore the lone pairs. What's the connectivity between two atoms? Well, it can only ever be linear, right? What are the idealized bond angles in between everything in here, though? Well, idealized, we'd still say that they are 120. What's likely the case, though? Likely the case is here, these angles would be bigger than 120, right? They'd like to spread themselves out a little bit more. Got it? Why? Because everything comes back to electrons repelling each other. Okay? Negatives repel negatives. You guys know that, right? So that's what's going on here. Okay? More examples, I believe. Okay? So on the left-hand side, right, this would be a perfectly valid Lewis structure, right? That's what you guys have been doing up until this point, right? If we talk about drawing molecular structure, we'll draw that out in just a little bit. Well, we can probably do it right now, right? But again, we have another example here where we don't necessarily have an atom in the middle, right? But if we're looking at the individual carbon atoms, we have three things around it, right? Three atoms around it, trigonal planar geometry for each carbon atom, okay? What are the idealized angles in all of these? They're all going to be 120, got it? So as we start to kind of work through this, how would we draw this as a proper molecular structure? Okay? When you guys go to draw your molecular structure on paper, we try to draw a molecular structure as close as we can to what the actual geometry is. Okay? You guys are like, okay, that makes sense. We try and draw things the way they look, right? So this is all trigonal planar. So what does that mean? That means all those atoms, what? Exist in the same plane. Can we draw a flat molecule on a plane of paper?
Yes.
Sure. Do we need to do any wedge and dash stuff? No, wedge and dash happens when? When you're in or out of the plane. Got it? So if everything's in one plane, do we need to do any wedge or dash? No. Okay, so how would we draw the proper molecular structure for this? You put your central atom. Okay, you try and represent your 120 degree angles as best you can. Okay, you put your chlorines, and you put your lone pairs there. Okay. So when you draw your molecular geometry, draw it as close as what the actual three-dimensional geometry is. Is everybody catching me on this one? Okay. This is our Lewis dot structure. That's great. That's fine. Nothing wrong with that. Our molecular geometry is going to look a little bit different. Okay. Should you guys get comfortable drawing both of those?
Yes.
Sure. Right? How many of you guys are already comfortable drawing all of those? Now, why would that be? One person. What's the big secret to this?
Practice.
Yeah. Okay. It's not like anybody in here was born with the knowledge of drawing tetrahedrons, right? But we're going to have to get used to it. Because I'll give you another hint. Right? It's even going to be on video, so you guys can hold me accountable on this. All right? So on the next exam, you guys are going to have to draw something that's in and out of the plane of the paper. There's going to be a tetrahedral question on there. Okay? How are you going to get comfortable drawing those?
Practice.
Got to practice. Okay, so is anybody gonna miss that on the exam?
Probably.
No, confidence is the key, right? Confidence. Okay? So when you draw the molecular geometry, as close as you can. Okay? Keep on moving. All right. So 4 total things. This is our tetrahedral electron pair geometry. Now we have to start worrying about things in and out of the plane of the paper. Okay? So we're going to do some wedge and dash stuff here. Okay? So if we have 4 atoms around the central atom, that's a tetrahedral lone pair and tetrahedral molecular geometry. You guys got it. Perfect example, the quintessential example, CH4, our good old buddy methane. Good. Right? Our good old buddy methane, CH4. What are the idealized angles in a tetrahedral geometry?
Oh, you want numbers?
Yep.
109.5.
109.5, right? So if I ask you guys for the idealized angles for anything, right, anything that has a tetrahedral lone pair geometry, your answer is going to be 109.5. But I'll be nice. If you guys even put down 109, that'll be all right. Okay? Okay? Can you fit 4 things that have 109-degree angles, right, onto a single plane of paper to represent its 3-dimensional shape? The answer is, unfortunately, no, right? So we are going to wedge and dash our way through this here, and I'll show you guys in just I believe on the next slide. I've got some space for us to draw it out. Oh, well, I kind of already did, but we'll do it on here then. Okay. 3 atoms, 1 lone pair. Trigonal pyramidal, okay, so trigonal pyramidal. So basically if you imagine a pyramid with 3 sides on it, okay, that's exactly what it looks like. Okay. Our best example is our good old buddy ammonia, NH3. 2 atoms, 2 lone pairs, bent again, so we're at another bent geometry here. Our good old buddy water. So water has a tetrahedral electron pair geometry, right? 4 things around it. 2 lone pairs, 2 atoms. Angles of 109.5 between everything, except, right? In reality, it's going to be a little bit smaller than that because those lone pairs are pushing things together, okay? Is everyone good on just the different delineations here on this stuff? Yes? Good. I see 3 nods. At 8 in the morning, we're almost 9. We're making progress. So let's draw this out, right? So you guys should be able to draw the Lewis dot structures for each of these. Okay, that's nothing that's different. Okay, Lewis dot structures are Lewis dot structures. Drawing the molecular geometry, aka drawing the stuff in 3-dimensional shape, is going to take a little bit of challenge, right? So here is the best rendition that we can have. Obviously, our drawings are not going to be that good. Well, I don't know, maybe your guys are, but I'm not a good artist, okay? So when you go to draw your molecular geometry, draw your Lewis dot structures first, right? That's always going to be useful. And then, okay, when you have to draw a tetrahedron, I don't care what atoms there are. I don't care how many lone pairs there are, okay? There's always going to be the shape is always going to look generically the same, okay? So we have an atom in the middle, okay? Let me color code this here a little bit. We're going to have 2 bonds that are in the plane of the paper, okay? We're going to have 2 bonds that are in the plane of the paper. Now you'll notice that I try to represent as best I can the 109.5 degree bond angle in there, right? You guys get what I'm saying with that? The reason why I spaced them out the way I did, okay? So 2 bonds are in the plane of the paper. 1 bond is going back, and the other bond is coming out. Okay? Your tetrahedron's always going to look like this. Okay? except when it doesn't. I'll show you what I mean in just a second, okay? But you guys get what I'm saying? This is what you need to practice how to draw. If you can draw this, then just fill in whatever atoms are in your Lewis structure, and you guys drew a perfect tetrahedron. I'll be happy, you guys will be happy, some of you guys will be grumpy, some of you guys will be sleepy, right? But at the end of the day, you guys have drawn the tetrahedron. Good? Thank you. What's that?
Will any of us be dark, sneezy, bashful, or dopey?
Some of us might be dopey. Okay? So once we have our generic shape for our tetrahedron, then just fill in whatever you guys need to. In this case, we had a carbon in the middle, okay? And then we just had some hydrogens there. Okay? That's it. Not too bad, right? Why do they call this a tetrahedron? Well, I think I mentioned this to you guys, but just for completion's sake, or just for a reminder's sake maybe, the reason why they call it a tetrahedron is because if you connect the hydrogen atoms on each face, right, on each side there, you'll create a four-sided geometric shape, right? It has four faces, tetrahedron, got it? It doesn't, and it, you know, for us it's a little bit useful, right, because it means it has, you know, tetra for you guys should kind of think about, there's four things around there. Okay, but don't get confused with octahedral, right? Octahedral has 6 things, but, you know, it has 8 faces. Okay? Cool. All right, so, one more example. Then I'll turn you guys loose to see what you come up with, right? So if I ask you guys to draw the molecular geometry here for ammonia, you have your central atom, okay? You're always going to have 2 things in the plane, one going back and one coming out. Yeah.
Should we memorize the fact that a tetrahedron with one lone pair is going to have an angle of 107.5?
Well, I'm just talking about for ammonia here. It actually does change,
Okay.
but I'll come back and mention those in just a second.
Okay.
But no, what I want you guys to know is the 109.5. I don't need you guys to memorize those specific numbers or anything. Okay, so now we got our nitrogen in the middle. Let's plop our hydrogens. Okay. And if we want to think about it, just for, I'll make it black here. If we want to think about it, that means our lone pairs are up here. Okay? And if you did that on the exam, I'd be fine with that too. Okay? But let's think about why this is a little bit strange for just a second. Remember, what are we representing with each of these lines?
Bond.
We're representing a bond, right? So kind of the way we have drawn, we have what? A bond to a lone pair, right? That's a little bit odd. So when we draw this out, typically, right, all we do is put our lone pairs right on top of the nitrogen like that. Okay? Fair?
Can we draw the lone pairs as Mickey Mouse ears?
No. Let's think here for just a second. So here's my nitrogen. My 2 bonds in the plane, and 1 out. My one in, my 1 out. Let's say that I wanted to put my hydrogens here, here, and here instead. Okay? Which means my lone pairs are back here.
That's not going to work.
Is this still a proper representation of this molecule?
No.
Yes. Okay.
But there's no denotation to show that the electron pair is like sitting behind the plane.
Oh. That's true. But what do we understand when there's a tetrahedron? Two things are gonna be in the plane, one out, so the other one has to be back, right?
Okay.
You guys catching me on this one here? Do you guys see how I drew this? I started out with the same generic shape, right? And I just filled things in. Got it? So does it really matter where we put the hydrogens? The answer is no, right? But 99.9% of the time you're gonna see it represented like this. Why? Well, then you can clearly see what the shape is and everything, okay? The relationship between this and this is just a rotation. But don't worry, we don't have to get into that stuff yet, okay? We'll get into that in...
Okay.
Okay, good, okay. We'll talk about how we manipulate things in three-dimensional space, okay? And for those of you guys who want to go on to dentistry school or that kind of thing, it's going to be a useful skill for you guys to learn, okay? All right? So see if you guys can come up with a good shape here for water. I think you guys probably already know the answer. Good, looks good.
I have a question.
Yep.
Why not put the lone pairs above and below the opposites and just make it linear?
What do you mean?
Because
He's saying, couldn't you draw it like,
Well, let me get him to ask this question. What's up?
because if we put a hydrogen on the left of the oxygen in the
Mhm.
middle and the hydrogen on the right, we just have lone pairs on the top and the bottom.
Yeah.
Like that, push everything this
So,
way.
so your question is, why do we want to draw it in a way that it's not truly represented?
Is that how it should be? And why is it then that we should draw it that way?
Are you asking about here for this? For the Lewis dot structure?
Yeah,
There it doesn't matter.
okay.
You're right. For that, I don't really care. Okay? But when I'm asking you guys to draw the molecular structure, then you have to try and represent the actual shape of it.
And why is it that the actual shape looks like that instead of what I said?
Because that's not what, the actual shape is not linear, right?
Why does it need to not be linear? Is it
Because you need to maximize the space in between the electron pairs.
Okay.
Okay? It's a good question. It's a good question, and I'll answer that in a little bit for you, right? As we get to a couple of the more complex geometries, we'll answer that question for you. So, good question. Okay. All right. So we'll put a central oxygen. Right, there's our generic, oops, I did that as red. Okay. So where can you put your lone pairs? Where can you put your hydrogens?
Anywhere.
Anywhere you want to, right? Could you put your hydrogens here? Oh, not like that. Put a hydrogen there. Put a hydrogen there. Then we could do something like this. Is that okay?
Mm-hmm.
Sure. Looks kind of, I don't know, looks kind of weird to me though, doesn't it? Right? But that's fine. That'd be perfectly valid. You guys could do that. Okay. For argument's sake, let's put the hydrogens here and here. Okay. We'll put the lone pairs there and there. Is that still the same thing? Okay. Now, if you guys drew that on the exam, I'd be fine with that. What you will see represented in all the textbooks, you'll see, whoops, you'll see this though. That's what we'll see drawn all the time. What's the relationship between this and this? What did I do with it? I just rotated it. You guys see what I'm saying there? I picked up the whole molecule and just turned it 90 degrees basically. Did I change the geometry of the molecules? No, right? So that's a valid representation also. But like I said, this is, if that's kind of tripping you up, then just draw it the way that I always do there, okay? Start with your simple tetrahedron, just fill in your stuff. And then you won't get it wrong. That's good too, right? Good? Okay. Everybody got the notes that they need here?
Mhm.
So see what you guys can come up with for that molecule. Give me the Lewis dot structure. Get me the molecular geometry drawn properly.
Is that an SI?
Mm-hmm. So see what you guys come up with for these 4 examples there. Don't forget your lone pairs and other problems. No. Okay, good. All right. No, I didn't get it, so. Good. Let me just, make sure you put one here on the buttons also. Just like, don't forget to put 2 long pairs around the buttons. Good. Good. Don't forget to put your lone pairs around the buttons. Good. No. Right now, don't have your plug with you. You have to, oh man, you have to take notes the old school way, huh? Good question. So, how do you know which one's in the middle for a Lewis dot structure? How do you know? There you go. Alright, so remember, this is based off of your Lewis dot structure. Right, so if you take a look at the progress of how to do things, for the Lewis dot structure, then the molecular structure. It doesn't change how the atoms are connected to each other. For which one? For the first one? How did you draw it for this one? No, it's SI, silicon. Yeah. I see what you're saying. No, it's just silicon, yeah. Not an IE interface. I got you. We'll get to that in just, I think the next slide deals with those, right? But not quite yet. So, good, you don't forget to put your little ears around there also.
They also have to do.
Yep. Yeah, you are still representing everything. Right? Good. So, looks good, but you might be missing something there.
There's no, okay. And this one feeds,
Oh, that's good.
but
Yep.
then I still have 6 left over.
Are you getting that one?
What am I getting this
Yeah.
from? So I have the 4,
Yeah.
the inside,
Yeah.
28.
Uh-huh.
And then this happens, and it says 8 around it. So these missing double bond will give me more, so I won't do that. And it will also kind of throw off our 8 rule. So it's like, what do I don't think it's gonna put that on here.
I think you're just miscounting,
Okay.
because if you need 32 total, right? 2, 4, 6, 8, 8 times 4.
That's true.
Yeah.
Okay.
So, that's all right. And it's good that you're checking, right? Now we need to develop a check to check the math, right? It's all right. Okay. You guys forgot to pay the electricity bill again. Come on.
It's because of my laptop.
Yeah, all right, guys, sorry, tuition's gotta go up. Maybe we got it all back? No. All right. No, you miscounted something. So silicon is here, and bromine. No. So I sure would love to give you guys the answers, but I don't have markers with me or anything either, but I can take a peek at what everyone's up to. Yeah, not too bad, but let's try, try and draw it more like a tetrahedron is what it is. So you're not far, right? I would give you credit for that, right? But let's try and polish it up a bit. That looks good. Yeah. This one, oops, sorry, be careful, you're missing something on
Oh, the charge.
there. And
What was the last one?
it was
Woo!
SO2. Yep. Where are your formal charges? And then go through the whole process of assessing the formal charges, that kind of stuff. And it's, right. Plus 2, right? That's kind of could be minimized in these formal charges in some way. So you guys, that's fine, right, but you guys are missing something along with this part. Well, remember, where is sulfur? I mean, sulfur's here, so we can go beyond the octet limit.
Oh, so that's what it is, the extra electrons, so that's what
Yes. Yep. So what happens if you draw a double bond between the oxygen and the sulfur? What does that do to your formal charges? carrying them out with them. It looks fine, but don't forget your formal charges, and don't forget to check to see if you can decrease your formal charges or change them in any way. The same thing with that. So be careful of that one. Very nice technique, but don't forget the plus 2 charge here. That's kind of a little bit unusual, right?
Oh, for Pete's sake.
I think that's maybe just the sensors. So see if you can reduce the more formal charges. So draw double bonds in between the two of us and see what that does. No, that's why I gave you that question. I never said if you have one single bond, it's gonna look like this. I said if you have 4 things, I don't care what they are, right? So it's not gonna change the geometry, but it is gonna change how many bonds you have and all this kind of thing. Yeah, you got the right shape in there, right? But we need to fix our bonds. Same thing for that one too. The right shape, but go through and check your formal charges, that kind of thing. Good. So now you have to put those double bonds in here, right?
Oh.
So we need to, so you need to represent those now also. Perfect. And then you got it. Very nice. Okay. Okay, good. And then don't forget your negative charges on the oxygens there. We need to show where the negative formal charges are.
How do I do that?
Just put a minus next to it. Yeah. There you go.
That's it?
That's it. Science. Yep, absolutely, yeah. That's the point of that one, right? If you see the double bonds or triple bonds here, make sure you show them in there also, right? Good. So like this, but maybe make one more double bond from one of those, and then you'll get rid of the positive formal charge on the sulfur. And then don't forget, if you have a double bond here, make sure you show it here also. Good. Now go through it and analyze your formal charges. Excellent. Now put your double bonds here. And well, they don't have to go on those two. I'm just saying make sure you show, if you have double bonds here, make sure you show them here. So, I like it. Make sure you show. Yes, yep.
But what about like?
Same thing there, right? If you
But what if they're,
right, that's the question, right? So, but
should I just switch which ones are? Is there all?
I'm gonna just think of the best way to answer it. The best way to answer it is it doesn't matter, right? Just because you drew them here, doesn't mean like their oxygen necessarily is that one there, right? You just have two, exactly, right? You just have 2 double bonds in between those oxygens. If it were me, and when I draw it, I'm just gonna put them there, because that's easiest to draw, right? I like that, it's good, it's good. It's good, that's just fine. The SO2 one, there's a little bit trickier than we might be ready for now, but you're fine with what you have drawn, right?
Formal charges down.
You do? That's good.
Is that for anything?
That's one of these key ideas in Gen Chem, so I'm glad to hear that. It is super duper important. All right, so it looks like we just got a little bit of time left, so let's start to put some ideas on paper here. So we got our silicon. Got our bromines. Just for time's sake, hope you guys understand, right? I'm following the rules in my head, right? I'm counting valence electrons, I'm doing all this kind of stuff with them, right? Least electronegative atom in the middle, silicon's less electronegative than bromine is, all these kind of concepts with them. So once we draw our Lewis structure, right? Let me just go back for argument's sake. I'm gonna show you guys what I do, and it's gonna be useful in another technique that we're about to learn in a couple slides also, right? So once I draw, oops, promise I'll actually finish a thought here. I forgot my lone pairs. Okay, so once I have my Lewis structure drawn, when I draw my molecular structure, I need to represent everything, all the information on Lewis structure in my molecular structure also. So formal charges, how many bonds there are, lone pairs, all that kind of stuff goes into it, okay? So there's no formal charges here, so we don't have to worry about that part. What I start to do is, let's use black. So what I start to do is say how many regions, how many things, right? How many things are around my central atom. I'm going to identify 4 regions of electrons. The only geometry that deals with 4 total things is tetrahedral. You guys got it? So, and this is going to help us when we identify the hybridization also. Okay, you're going to see me do these boxes. I'm going to ask you about regions or domains and this kind of stuff. So 4 things around a central atom, tetrahedral. Once I know it's tetrahedral, I can draw my basic geometry. I can fill in my bromines where appropriate. And I fill in my lone pairs. Okay? Good? Not too bad, right? And my good old buddy SO42 minus. I'll take a little bit of a an extra time here, right? So I saw most of you guys had this. I think I talked to everybody about it. That's a fine Lewis structure. Nothing inherently wrong with it. We didn't violate any rules, right? But remember, now the question is, not only did we draw a Lewis structure, it's did we draw the best Lewis structure, right? The one with the least amount of formal charges, the lowest amount of formal charges, right? If we go through and assign our formal charges here, right, we would see that every oxygen has a -1, and the sulfur in the middle has a +2, right? And we can minimize that by making some double bonds. And when we do that, when we do those double bonds, come on, let's erase. Now my sulfur and those 2 top and bottom oxygens have a 0 formal charge to them. Got it? Now, here's a quick side note. Why did I pick those top and bottom ones? Could I have picked the ones on the left and the right? Could I have picked the top and the left or the top and the right? What's the relationship between all those? Those would all be resonance structures, okay? So good example molecule here to go through and draw resonance structures with, okay? Once we have that, now we need to represent everything in our Lewis structure, in our molecular structure. I have 4 total things. It doesn't matter if they're double bonds, triple bonds, or lone pairs. I've got 4 things around my central atom. Identify that, I know it's tetrahedral, sulfur in the middle. I draw my generic shape. I fill in my oxygens. And I need to show my double bonds, okay? Remember, you need to show everything in your Lewis structure in your molecular structure. If you have double bonds, show your double bonds. If you have lone pairs, show your lone pairs. Yeah?
If we have a double bond of a dash or a wedge.
Yep, perfect, right? So right before we go, in the last 10 seconds here, if you guys have a double bond that's wedged or dashed, usually the way it's represented is one of the lines is dashed and you just put the single line next to it like that, okay? Good? Cool.
Do you write in the charges?
Yes, yep, and we write in the formal charges. Good. You're welcome. I will see you guys on, we'll have I'll pop up another quiz for you guys for next week, probably on Wednesday. for you guys to get through. It'll be online like the last one was, okay? Yeah, go back to the, go back and take a look at that.
Birthday.
Okay, so see what you can come out, right?
Ready to retire?
I gotta go to the next slide.
Do you know what I say?
Yeah.
Follow through your steps here, electromagnetic in the middle, on steps.
It's in the calendar.
That there, you'll see that you,
Freaked out this morning because I looked and it said Mr. Philly Books and then one left and I was in the call for semester.
Yeah, everyone's
I
like
need
panicking.
to.
I'm panicking.
Yoga.
Effect.